In this video, we're going to talk about Simpson's Rule. Simpson's Rule is a method of numerical approximation, so approximating an area under a curve, similar to the Trapezoid Rule or the midpoint rule that we've seen before, but we're going to make this one as accurate as possible, or more accurate than what we've seen before. So let's think back of what we've already seen. So we talked about the Trapezoid Rule and the midpoint rule, and we talked about how they were over and under approximations. And in particular, we saw that anytime the midpoint approximation was an over approximation on these types of curves, that our Trapezoid Rule was an under approximation, or vice versa. So one thing that you might say, if you know that that's the case, you could take the average of the two. I could average the over approximation with the under approximation, and it would probably give me something closer to the middle, which is going to be more accurate than either of the two individually. We can actually go one step better than that, because not only do we know that one's an over approximation and one's an under approximation, we also found out in the last video that the midpoint rule's error bound was twice as accurate as the trapezoid's rule's error bound. In other words, that's saying that for most curves, or on average, the error of my midpoint rule is going to be twice as good. The approximation of my midpoint rule is going to be twice as good as the approximation of my trapezoid rule. So if I were to do an average, it would be nice to do a weighted average, one that took into account the midpoint rule being weighted twice as heavily as the trapezoid rule. And that's exactly what Simpson's Rule does. So we define Simpson's Rule to be the weighted average, where I take the average of the trapezoid rule and the midpoint rule, but instead of just averaging, taking the sum of them and dividing by 2, I'm going to take one copy of the trapezoid rule and 2 copies of the midpoint rule, because the midpoint rule is twice as accurate, and then divide it by 3, because I have 3 different approximations being summed on top. One thing I left blank here, sort of intentionally, was the subscripts. And the problem, that's sort of solved by Simpson's Rule, is that the endpoints for the trapezoid rule and for the midpoint rule are different. That when doing a trapezoid rule, I look at the 2 endpoints, and for midpoint rule, I look at the point in between. Simpson's Rule solves that by taking the whole interval, dividing it up into n segments, and for the trapezoids that we're using are going to be sort of doubly fat. That my trapezoids are going to go from x0 to x2. That's the width of these intervals. And so it means that my midpoint is going to be the value given here at x1. Sort of solves the indexing problem, but it means that I have half as many trapezoids as I had increments. So I call this n divided by 2. So for example, if S8 is using 4 trapezoids and 4 midpoints, this is also n divided by 2. And if that's unclear, let me add a picture. I think the picture might help. So in this example, I'm going to break up, I've broken up my entire interval from A to B up into n different segments, but each of my trapezoids are going to be, whoops, that's a preview. My trapezoids are going to be twice as fat. So here's my trapezoids that I'm using for this approximation. Similarly, the rectangles that I'm using for midpoint rule are also going to be twice as fat. That these are the rectangular approximations that are used within the weighted average for these midpoint approximation rectangles. And while I'm talking about the geometry behind this, I think it's important to point out that there's actually a geometric implication for what Simpson's Rule is, beyond just the weighted average of the trapezoid and midpoint rules. That if you were to describe each of these regions, instead of being a trapezoid or a rectangle, that they would have a rectangular base, but if you made, let's see, I need one more color, don't I? A parabola out of the 3 points formed by the endpoints and the midpoint. That's exactly what Simpson's rule is doing. So on this one, suppose that I made a parabola that went through these points. 3 points uniquely define a parabola. Simpson's rule is measuring the area under these curves that are parabolic, which is a cool way to think about it. And it's going to be really close to the actual curve, because notice that this looks almost parabolic. It looks like a quadratic function, that it's going to be very close to what you would get if you pick these 3 points. You have to get like a really jumpy function to see how these parabolas wouldn't line up exactly with the function itself. So how do we compute this? That's the idea behind Simpson's rule. It's the weighted average of the trapezoid rule and the midpoint rule, because the midpoint rule is twice as accurate. I can rewrite this as 1/3 t sub n divided by 2 plus 2/3 of m divided by 2. And we have some fixed ways of talking about these trapezoids and these midpoints, and I'm going to walk through the computations sort of step by step. So recall for our trapezoid rule, that's going to be the base times the average of the heights. And there are a couple of things that I want to point out. In this case, the base isn't just delta x. Delta x, I guess I should label this. Delta x is the same thing as the width of each of these things right here, and I could label up here that delta x is equal to b minus a over n, where n is the subscript on Simpson's rule. But because these are twice as fat, our base is twice as big. And then the average of the heights, notice that these heights are only going to be the even numbered indexes on x, because we're only taking the first and the second, or I guess the initial and the second. The x sub 1 is the midpoint, and so it's not going to be included. And if we do this over and over, so this is the first trapezoid, the area of the second trapezoid is the fat base times the average of the heights, where both of those are even values. And you continue on all the way to the very end, where it's the fat base times the average of these two heights. You notice algebraically that these 2's cancel, and so we can simplify this rule to look more like our previous rule. It's the width of half of the base, right, of the trapezoids, which is b minus a over n, plus the first, and then 2 copies of all of the interior even indexed x values. And you get 2 copies because the height is used once for this trapezoid and also once for that trapezoid. Our midpoint is a little bit easier, I think, that the area for our green rectangles are going to be these fat bases, which is the same base that we had in this trapezoid, plus the midpoints of the heights. But notice the 2 doesn't cancel with the average for the midpoint rule, so we get our midpoint rule is just delta x times 2 copies of each of the midpoints. 2 copies because it's twice as fat for Simpson's rule as compared to this midpoint rule using half as many rectangles. So what does that give me? This is my formula for t sub n divided by 2 and m sub n divided by 2. Continuing on, we know what Simpson's rule was. I'm going to put all these computations all on the screen at once. Let's see. This 1/3 of our t sub n formula, which is right here, plus 2/3 of our m sub n divided by 2 formula. I end up with this 1/3 of what I have written up here, plus 2/3 of what I have written down here. I can combine that all together, and we get this nice final answer. Our nice final answer tells us that Simpson's rule, S sub n, is equal to, I can factor out a delta x, and I factor out 1/3 from each of these, but notice that means that there's a 2 remaining, and this 2 distribute to each of these terms. So when I add up each of the pieces, I end up with 1 copy of f of x naught plus looks like 2 copies of f of x1, but it's not actually 2 because I need to weight it as the weighted average. I end up with 4 copies of f of x1 plus, maybe, what am I doing? I'm going back and forth so that we go in numerical order when summing these. Plus 2 copies of f of x sub 2 plus 4 copies of f of x sub 3, 4 because of the distributive property, plus 2 copies of f of x sub 4 plus 4 copies of f of x sub 5 plus dot 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 plus, and I'm going to continue this 4 2 4 2 4 2 4 2 pattern until I get to the very end. Looking here, I only end up with 2 copies of f of x sub n minus 2 plus 4 copies of the odd numbered ones, 4 copies of f sub x minus 1 plus a final single copy of my final value. Whew! So that's my formula for Simpson's rule. And keeping in mind the fact that delta x in this case, I'll write it down here, delta x is equal to b minus a over n, the width of a single rectangle, not the width of these double wide fat rectangles. So the thing to keep in mind when looking at this formula, it may seem like a mess right now, but when I think of it in my head, it's 1 copy, then 4 copies, 2, 4, 2, 4, 2, 4, 4, 2, 4, 1. And I'm pointing out that all of the odd ones, we always have 4, because the odd ones are the midpoint ones and we want them to be weighted heavily. Have a coefficient of 4, whereas the even ones look like the trapezoid rule. The even ones start 1 and then go 2, 2, 2, 2, 2, 2, and then back to 1 again. So maybe this is my thought cloud. Maybe that's not a helpful thought cloud for you. Let's go ahead and look at an example. So we're going to approximate the integral from 0 to 2 of e to the x dx, and we're going to use S8. So I'm breaking this interval, maybe I'll even write it out. My delta x in this case is b minus a over n, which is 2 minus 0 over 8, which is a fourth. And I've already labeled out all 8 of those. And when thinking about this, S8 is going to be the weighted average of T4 and M4, because I'm going to use half as many for my trapezoids and for my midpoints, and I can visualize what's going on here like this. So looking back at our formula, S sub 8 is going to be equal to delta x over 3 of 1 copy of the first thing, f of 0, plus 4 copies of the midpoints. We want 4 copies because it's weighted more heavily. 4 copies of f of 1/4, plus 2 copies of f of 1/2, plus 4 copies of f of 3/4, plus 2 copies of the endpoint f of 1, plus 4 copies of f of 5/4, plus 2 copies of f of 3/2, plus 4 copies, I know this is a little tedious, of f of 7/4, look, we're almost done, plus just 1 copy of the endpoint, 1 copy of f of 2. Whew! And you can see sort of embedded in here, I'll underline in green the midpoint ones. The midpoints are all multiplied by 4 and I can draw those dots on here, whereas the trapezoids go 1, 2, 2, 2, 1. That's the pattern. So now we're ready to finally compute this. I could write this all out again, but I think that that's tedious for you. I think something that's more interesting at this point is I'm just going to write down the decimal approximation. What do I get out? Recall delta x in this case is 1/4, so 1/4 divided by 3 is 1/12. 1/12 of all of this mess. I'll plug it into my calculator. F of 0 is e to the 0 plus 4 copies of e to the 1/4 plus 2 copies of e to the 1/2 plus 4 copies of e to the 3/4. At this point you're saying, Carolyn, why aren't you using an Excel spreadsheet to do this? Because that's something that is totally reasonable to do, that I might just enter this formula into a GeoGebra applet or an Excel formula, and that's something that we'll talk about in a subsequent lab, actually. Whoops. 2 times e to the 3/2 plus 4 times e to the 7/4 plus 1 copy of e squared. And let's check. So I have e to the 0, 4, 2, 4, 2, 4, 2, 4, 1. Great. I press enter, and now I'm going to divide that. So my numerical approximation at this point is 6, 7. I'm just recording it as an approximation. I divide that by 12 and end up with an approximation of 6.38919337. And we can compare that to what we found last time around. Notice that this is my S8 approximation. And you said, we didn't actually need to do all of this work because we had some work from our previous examples. We saw previously, and we'll check, we'll verify, 1, we see that this is extremely close to the actual value. This is when we actually computed the integral on the same example previously, that our integral value is very close to what we get here with our Simpson's approximation. And I can also check that it is indeed the weighted average of these two things. Because I already knew M4 and T4, I could have skipped all of this work, and I could say, oh, that means that S8 is going to be 1/3 of T4, which I have written down right here, 6.52161, plus 2/3 of M4, which we got as 6.32299. And plugging those values into our calculator sort of as a verification that we are doing what we think that we're doing. My weighted values, 6.52161 plus 2/3 of 6.32299. Whoops. Oopsie. Gives us our answer that we thought we would. I added an extra parenthesis, and now I'm going to have to retype all of this because I pressed the wrong button on my calculator. You, of course, would never press the wrong button on your calculator, and so you wouldn't run into this issue like I did. Great. Gives us something that's about equal to 6.38919. And again, given my approximation that this is what I think that it should be. So, if you've already computed T4 and M4, it's not that much more work to compute S8. Let's look at, one final piece of information. Something that we talked about last time was our maximum error formulas. We'll talk about this time maximum error formulas. And you would expect that my Simpson's approximation would be more accurate than either of these individually, because they're weighted averages of these that have been chunked into smaller intervals. But our formula for the error approximation is very similar. It is always going to be bounded, so less than k4 divided by b minus a to the fifth, k4 times b minus a to the fifth divided by 180 times n to the fourth. A and b, again, are our upper and lower bounds of the integration that we're doing. N is the number of intervals, but instead of using k2, which is a second derivative approximation, k4 is a fourth derivative, and maybe this is notation that you haven't seen for a little while. This is really f1, 2, 3, 4, f to the fourth derivative, of f. So whatever my function is in my integrand, I want to make sure that its fourth derivative is bounded by some value, k4, for all x's in AB. And it gives you a very, very accurate value in terms of how bounded the error is.